Let's talk about ichnofossils. So, ichnofossils are going to be trace fossils. A lot of those take the form of burrows, and there are probably more ichnofossils than body fossils, almost certainly, because one creature may make multiple burrows, and it doesn't take exceptional preservation to preserve an ichnofossil. It just takes rapid covering and not being disturbed. Yeah, and then you will get the ichnofossils. So there are many areas for which we have ichnofossils, but we don't know the body fossils that would have made the ichnofossils, which is kind of cool. One thing we do see, though, is shown here from Kansas University, and there are particular points offshore, and each one is going to have its own ichnofossil zone. And so they'll name these after one particular ichnofossil from that zone, like this is Scolithos, and Cruziana is, I think that one is trying to be Cruziana. It's a little hard to see. Zoophycos is this guy for sure. I think Nereides is this one, or maybe this one. It's sort of a back and forth kind of ichnofossil, if I remember correctly. Yeah. So these are each probably made by a different kind of organism, and they are showing the behavior of that organism or the place where that organism lived, which is information that you would not get from a body fossil. You would have to try to infer that by comparing it to modern fossils, or get really lucky where you find the body fossil in its house, basically, yeah, which rarely happens. It does for certain types of infaunal organisms. You will get them in their burrows, but everything else, especially pelagic things, there's no chance. They don't really have a home. Here is an awesome ichnofossil, and this comes from a paper by Dean Lomax, who we like a lot, and have worked with in the past. This ichnofossil is a what they call a death march. It's Mortignes, if I remember correctly, and that is a specific type of ichnofossil where you have a trackway and it ends with the dead organism. And so you can see its life, you can see its final minutes, and you can see its death. And these fossils may only be able to be dated to plus or minus, half a million years or a couple million years. But what you've got here preserved are maybe 5 or 10 minutes from an animal's life and all the events that happened in those. And these are precious, incredibly valuable things. So let's have a look a little more at this particular one. It'll come from this paper. So here is the end. You get the fossil of the animal, and with this you can actually see what's going on. So this is a modern horseshoe crab. This is what's called Limulus. This one is Mesolimulus, which is the Mesozoic equivalent of it, and one of the ancestors presumably, or at least a sister group of it. Looks pretty similar. You can see it's got this long sort of tail spine. I'm not sure if they call that a telson, but it's equivalent to that. And you can see that's what's making the drag mark in the center. You can see on the side you've got little marks that look like little, actually, kind of drunken feet. It's sort of stumbling and wobbling. They're not going in a straight line. And that is the last moments as it's stumbling forward right before it dies. Those are going to be made by the legs, and there are paired arthropod appendages that sit under the carapace up here. Mouth parts are located under this part, and the eyes are here and here. So, what we think happened to this one is that, well, interpreting the fossil evidence, yeah, with our best detective, hat on. Here we get the start of the trail, and it looks like a plop. It looks like this creature was dropped in from above. Now, there wasn't anybody around to be picking these up and, chucking them in the bay, so probably we're looking at something like a current, a rogue wave, a storm, something washing this creature out to sea. And then for some reason, it is dropping down, 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 and it is landing at the bottom. And these are normally found near shore, and this formation is believed to be deposited well away from shore. So yeah, it had to be carried a long way, and then it looks like it didn't make it back. And so here you get the drop, and you get the creature kind of moving around, trying to orient itself, and then it sets off in a direction. And so here you have the little tail drag, effectively, and here you have the paired walking legs moving. Now, the other thing to know about this is an area where we get exclusively very well preserved fossils. When you get fossils, it's kind of rare that something ends up at the bottom of the ocean, but it's an anoxic zone based on the kinds of minerals that you get in the actual rock itself. It doesn't appear that there was much oxygen in the environment, and that's certainly borne out in the quality of the fossils, which are frankly amazing, some of the best ones. So yeah, plop, land, and start off in a direction. Probably this creature can't breathe. And so also probably it is very, very dark down here. Probably too dark for the compound eyes of Mesolimulus to see anything. Here we see it gets up to a point and it's not making any progress. It hasn't made it back to the land and it's not any easier to breathe. And so the creature stops and you got little steps as it's going turn, 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 like a nervous student driver inching the wheel along like that. And then it sets off, roughly a right angle, and here's our tail drag again. Here you can see there's the interpretation. Here is the trackway, and so our tracks are leading up to here. And at this point, it just kind of turns around the circle, like what is going on? Still not any easier to breathe, running out of oxygen, and pitch black. And what are you going to do? You just got to just keep swimming, like they say in Finding Nemo. Only in this case, walking. So our little crab goes walking off in this direction. And here you start to see the effects of low oxygen. The footprints get weird. They're kind of spaced out. They kind of wobble side to side. Look at this sort of snaky path. It is stumbling. It is just having a very hard time going along the bottom. You can see that the tail is partly up and then partly down. You'll get a drag and it'll be up and then a drag and it's up for a while and then a drag. This is a very disoriented crab having a hard time. And you saw the end. Here's the end. It ends right there. And that is the crab fossilized where it died. This is a very rare case where you get both the ichnofossil and the creature that made the ichnofossil, or you can call it a body fossil, in essentially the same context and the same fossilization, and they both got preserved. A lot of things could erase one or the other, particularly the body fossil because it's made out of nutrients that everything wants. But that didn't happen here. Probably because of the anoxic environment and the very, very limited number of creatures that can survive down there, which tend to be real small and may not be able to effectively break down a creature like this. And also, it's in a weird place. If you're in the anoxic zone and you're waiting for detritus to come in, you're probably going to be right at the edge, waiting for something to just fall down the slope coming off the coast, which you could then eat. That would be the highest percentage chance of success. The odds of this happening are pretty small, and yeah, here's one. There are a couple others, but not many. And then imagine the paleontology rather. You have to expose this entire giant trackway. You have to then get it into pieces. You can see all the pieces it was broken into. So that you can transport this out. This is a lot of rock. This is like enough rock to make a driveway and maybe the sidewalk that goes with it. Maybe a little more than that. And it's all part of the same fossil. Imagine a museum trying to display this. They might need an entire extra room to be able to do that. And you can kind of tell, it looks like they're getting this out and they can't even adequately light the fossil from end to end. See, it gets a little darker here every time there's a big join. Probably because, yeah, exactly that. It is enormous, and they're getting this out on a laboratory bench and just trying to get it all together so they can get the photographs so that they can make this. Yeah, you'd have to photograph this from, honestly, a drone or something like that. And then you wouldn't get as much detail in there. Interesting little ichnofossil story. Here's another famous kind of ichnofossils. So these are the three ichnofossils that you get with trilobites, and any other organism that has trilobite-like lifestyles can potentially leave these. So it's showing the different modes of life. So the trilobite will be walking along here, and when it's walking along, just the little tips of its paired walking legs are going to be dipping in there, and so you get basically just like little footprints on either side. As it is, at some point, it decides to essentially burrow kind of halfway into the muck. And we think this may be a feeding type behavior, or potentially there are other explanations, but that I think is most reasonable. And so it is going to sort of burrow through just the top layer, so staying sort of partly submerged like a submarine with its periscope up. And driving through the top layer of muck, which is where all the new stuff just landed, and so potentially where the highest nutrient concentration is going to be. And presumably they're eating as they go through that. Most likely, the idea is that they would be guided by something like scent, but the underwater equivalent, so a sort of chemotaxis for dead, rotting things. And then at some point, you get these resting traces where the creature will make a little burrow. It'll sort of dig in a little further. There are a couple fossils of these, and it looks like their eyes are just up here at the surface, so they can just see out, because their eyes are kind of on top of their head and usually stick up a little bit. This could have been very effective as a deterrent to predators if the trilobite was doing that. And so we have Diplycnides when it's walking, Cruziana when it's sort of cruising through the top layer of the sediment, and the resting trace is Rusophycus. Yeah. And you can see here the imprint of the middle segments, and potentially there are gills paired with each leg on a trilobite, and these might be the start of the gills, or else the place where they connect to the body. And trilobites, you will remember, are rarely preserved with any of their appendages, mouthparts, gills, or legs intact, gills least of all. But there are a couple extraordinary places where we do get that. And when we do, it is fantastic. And we just have to fill in that missing information from those few fossils for all the rest of the multitude of trilobites. There are thousands of trilobite species named. They appeared to change fast. They appeared to be highly localized. They were super numerous. These were the kings and queens of the ocean bottom. Good for them. Shown above, this is Scolithos. This is an ichnofossil that has been taken at different times and places as the marker for the start of the Cambrian. If you see Scolithos, you are no longer in the Ediacaran. You have entered the Cambrian. And it's just a little set of, they're like tubes. They're pretty straight, and they can be quite close together. So some sort of worm-like organisms, although almost everything is either worm-like or has a worm-like stage in its development. So that doesn't narrow it down much. Presumably living either in high density or living in a burrow and then moving right next door and right next door and right next door. But I think probably a lot of them living together is a better explanation. Just in terms of the amount of energy you get for the amount of gain by moving, half an inch to the left. So here are some of those little images. And so there's another Diplycnides. Here's a Cruziana fossil, and here's a Rusophycus fossil, all on its own. There you go. And this one actually preserves a really nice outline of the underside of a trilobite. You see it's only messed up a little bit up here where the trilobite walking legs and gills would have been, which kind of makes sense. The mouth parts are up here. They're partly preserved in this fantastic mold. So the trilobite was very still, except for its legs, which it probably needed to get in and then get out again. The sediment must have been extremely fine-grained and was covered over before it got disturbed. So, kind of special preservation, but one individual could, bed down here tonight, move over, bed down here, bed down here. One individual could leave lots of ichnofossils if the conditions are right. All right. So, what do ichnofossils tell us about the Ediacaran to Cambrian transition, which is the Proterozoic to Paleozoic transition, is another way of saying it. Which is what, and here they're saying not just Proterozoic to Phanerozoic, which is, so it's actually Neoproterozoic to Paleozoic. Proterozoic is the two eras that come before the Cambrian, and Phanerozoic is the eras from the Cambrian onward. So this extraordinary place, and I believe it is in China. Yep, there we go. It has the transition as the Ediacaran ends and the Cambrian begins. And we have, authors have been looking for a major sort of upheaval, like volcanoes, like a major change in the rocks or nutrients. And there are some kind of weak evidence for something like this, like a geological catastrophe. But it looks as though the main driver of change from the Ediacaran to the Cambrian is new animals that have developed with new modes of existence, and they are just so good at their jobs that they basically make it impossible for Ediacaran organisms to live. The idea is that Ediacaran organisms were very dependent on the biofilm, and they tended to live on top of it or burrow very shallowly just along the surface of it. And the Cambrian organisms, Cambrian type organisms, are burrowers, big time burrowers. Burrowers, meanderers, they dig holes, they mine for food. And you can imagine during the entire Ediacaran, all of this sort of food, usable nutrients building up underneath the biofilm as it dies and rots and more biofilm grows over the top of it. And so this is a giant, unexplored, like, reserve of nutrients. And the Cambrian organisms get in there, and when they do, it probably disturbs or destroys a lot of the biofilm. That's the thought. And then once that happens, there's basically no way for a slow-moving, farming type, essentially, Ediacaran organism to exist, because there's nowhere for them to exist. There is competition, and so that's the idea. The competition drove the start of the Cambrian explosion. So you have evolution constantly, and then once these new, maybe even just behaviors, maybe the body plan differences may have caught up after the behaviors, potentially. Yeah, interesting question. Anyhow, at the site you can find Ediacaran type fossils, like the normal kind of things. Fronds, there's a Dickinsonia morph that's there. Some of the small organisms. Then you can find some of these trace fossils coming in. And this is the point where we're probably exiting the Ediacaran, at least locally. And we're going to draw the line up here. And the line is somewhat arbitrary, has to be said. It's going to be based on a particular transition in a particular place. But you can make the case that, the Cambrian is really getting underway right here, or that this is transitional. This is marking the end of the Ediacara-style organisms and the beginning of their replacements, which are things that would include us. So, what do we see there? Here are some of the Ediacaran organisms, and look at that. Here's some of these little fronds looking great. Here are some other fossils. You got Aspidella holdfasts. We looked at one of those, which are believed to be, they draw them sometimes like a bulb of garlic, sort of halfway seated in the sediment. And there's a lot of speculation as to what they are. They appear to be animal-like, in the sense that they are similar to the other Ediacaran, what we call megafauna, like big animals. And then we've got some interesting traces down here. So this is a sort of a scratchy lines that go in curves. So this is some kind of maybe burrowing worm that's just sort of figuring things out. And here's a fossil of a series of holes next to each other. And this is again thought to be an ichnofossil. It's possible because remember, Ediacaran style preservation is kind of like ichnofossil preservation. You have a death mask, you have the shape of whatever it was, if it was an ichnofossil or a body fossil, and all the original is lost. So yeah, kind of a stationary ichnofossil is what you get in those cases, or ichnofossil of a stationary thing. All right, here are some of the other fossils that you get there. And look at this. We've got a little aspidella down here at the bottom. And we've got a bunch of worm trails that are coming around, maybe honing in. This may be one that died and started to rot. And look as though they may be entering this, or at least bumping into it if it was still alive. So potentially that is one creature eating the dying remains or dead remains of another creature. Which is, I don't know. At some point, the difference between scavenging and predation depends on how lively the organism is. And when you got organisms that don't move, it would take a very similar tool set to do both. So it may not have been a big transition there. But you can see little tracks that appear to have legs. Now, we don't have anything from the Ediacaran, any body fossils that appear to contain legs, and these are from right on top of where you get the Ediacaran type organisms. So they're a little later. And so are these the first things like arthropods, maybe panarthropods? Good question. But this one's walking along. Here it's burrowing down a little bit. And then this little circular thing down here looks as though it has made a burrow. So it's walked along and found a place to sleep. So you could call this a Diplycnides with the little footprints, little pinkies touching touching the mud at the bottom of the ocean. You could say this is similar to a Cruziana, and you could say this would be like a Rusophycus, essentially. Ichnotaxa are named with a genus and a species, even though they are just traces. They're not bodies. And so we can't put them on the tree of life because that wouldn't really make sense. But they are definitely made by something on the tree of life, and this is how we categorize them. So a lot of these ichnofossil genera will have ichnus in there. So here's a strepped ichnus ichnofossil shown up here, which is some sort of burrowing or resting trace. Here we have from a different site at the transition from the late Ediacaran to the early Cambrian. We think these are still probably late Ediacaran. And this is from the same site, but the previous paper to the other one. And you can see these little, what look like paired appendage footprints walking along here. And here are some other really nice ones. And you get the little paired appendages leading up to this point. This is presumably either a resting or feeding trace here at the end. Yeah, very interesting. And here's some more. And so these are before we have body fossils. We don't know what they are. They're kind of in that window between Ediacaran exceptional preservation, like Ediacara Hills style, White Sea style, and some of the Cambrian, like Chengjiang or Sirius Passet up in Greenland. Yeah, love to know what these creatures are, and you can kind of imagine them based on the traces, but it would be nice to actually see, because there are probably some features that we are missing here. All right. Then once we get to the start of the Cambrian, that's going to be marked by an increase in what they call bioturbation, which is living things creating basically turbulence, just like paths in the mud, as they are moving, as they are feeding, as they are mating, doing all the things that organisms do. And you'll get these sort of searching patterns, like searching to the left, searching to the right, left, right, and so on. Probably looking for food is what we would imagine. Are they burrowing out a little house to live in? Are they laying eggs in chambers? Unless we have body fossils, it is very difficult to actually be sure, but there's a lot of information in ichnofossils, and it's a different kind of information that you do not get from the body fossils. Okay, here are some Ediacaran body fossils, or rather ichnofossils, and you can see this sort of peculiar movement. So it's almost like maybe a worm moving along and pushing a bit of sediment. Is this a segmented creature? Is this just the front of the creature that's moving along? It's hard to tell. Here's one that's making a sort of a zigzag shape. Here's one that's making a kind of a corkscrew shape. And yeah, we can imagine the organisms that would have made these. And so this is part of the fossil record. Ichnofossils are fossils. Yeah, there. Stamp that in the book. It's just they are fossils of behavior, generally. The effect of behavior, or the impact of behavior on the environment, specifically. Here are some others. You can see we get these burrow fossils, and you'll have multiple layers here in the burrow, which is interpreted as this is an animal that went down and then came up, maybe to hunt or something, and then went back down in, and sediment built up as it was coming back in, and up and down and up and down and up and down, just like that. So it did that for a living. Yeah, it's possible. Along with some other ichnofossils there from the same formation. Here are some ichnofossils from the Cambrian explosion, like the very early parts of it, which we think show paired appendages. So something like a trilobite, but way before we get any fossils of trilobites. Was it a soft-bodied trilobite? Was it something related to that? Was it something different that eventually turns into the trilobites? Was it a sister group to that thing? Hard to say. We can just say that it is moving along the bottom and leaving its impressions on there in a way that trilobites would later do. So similar lifestyle is the idea that we take away from these ichnofossils, along with very peculiar things. So this one is maybe moving like a sidewinder snake. We've got a series of little tracks where it's maybe moving itself along. Here we have some leg imprints, like a Diplecnides. Here we have a nice little tube, which is sort of a burrow going through. This is the inverse of the actual fossil. This is sticking up where the actual fossil would have been an imprint or a hollow tunnel. Here and here is Scolithos. So these are from Pennsylvania, from a particular rock in the Chickees Formation. And these parallel tubular burrows are taken as the things that actually mark the boundary, the lower boundary of the Cambrian, at least in some places. There are more formal ways that we do this now, but at one time these were a biomarker that says that you are definitely in the Cambrian. Now, there's probably somewhere where you can find something similar to this from the late Ediacaran, or maybe this is an organism that was only extant in the Cambrian. But it is definitely, triumphantly a burrowing organism. Look at those long, straight burrows all next to each other. Have you ever seen pictures of garden eels where they all have little holes and they all stick their little heads out of holes and look around, usually among the seagrass? Picture something like that, although probably not a chordate, because chordates were very rare back then. So, I hate to say it, some kind of worm. But the most common worms at the time, worm-like organisms, at least in the places where they are preserved, tend to be preapulid worms with that sort of eversible proboscis that's kind of spiky up there. Yeah, we think those were detritivores and lived at least partly buried in the sediment. They could stick their little proboscis out when they needed to feed. Ichnofossils tell stories. So here are Lochia ichnofossils, which are thought to be the traces where bivalves were planted in the mud. And if you've ever been to the beach, you know that when the tide goes out, the clams, bivalves, things like that, will tend to bury themselves just so that they can stay moist and protected. Nobody wants to be picked over by a bird, even though this is way before there's anything like a bird, I believe. Yeah, not completely sure on the age there. But look, here's a bivalve, and that's doing fine. But then this is a bivalve that we think might have died. And when it died, it started to rot. And when it started to rot, it started to stink. Yeah, if you ever brought shells home from the beach that had something in them, yeah, you know what I'm talking about. And then look at these worm traces. These worms are working their way, following the chemical gradient right over to this dead, potentially clam, I guess, bivalve, and presumably feasting. And so some of these would be traces from it going in. Maybe this is a trace of it going back out. Here's another one coming up, getting a little snack, maybe coming back out over here or out over here. These worms would only make traces when they are in the ground. They could swim along the surface, and that would not leave a trace in this particular rock. This is kind of a subsurface ichnofossil. But yeah, neat little story. Here's another neat little story from Silaker and Silaker, 1984 or 1994. This is a little trail that we think was made by a bivalved mollusk, something like a little clam. And these will move by opening and shutting their valves. And so you have this little sort of pattern. It's got chevron-like patterns, which we think are from the opening and shutting valves. And it's coming from over here. And we think this is maybe like low tide is coming, or it's nighttime, or it needs to move for some reason. And so it goes across a dune, down to the valley, across another dune, doesn't like something over here, turns around, comes back across the same dune, maybe because it doesn't really know where it's going, and finds a spot that it likes, and then it burrows in there. And so you get a lochia impression where this little bivalve buried itself. And then there's no fossil there, no body fossil, which means that it buried itself and it didn't die. And that, my friends, is success. That's why you bury yourself. Yeah, so you don't die. There you go. At least when you're a bivalve. Other kinds of ichnofossils, coprolites, which are fossil poo. Yeah, these are some examples, and they are going to preserve the shape of the intestinal tract of the animal that made them. So these are all from vertebrate animals, and there are actually ways to classify these and to use these to understand about the biology of the organism. You can dissect coprolites, and if there are fossilized pollen or traces of whatever they ate, you can reconstruct the diet. Because, as is today, like if you go to, I don't know, some kind of buffet restaurant, you don't eat everything on the buffet. There are particular things that you like, and those may be different from what somebody else at your table likes or across the restaurant. And that's okay. That's what keeps these places in business, I think. Yeah. Although they seem to be going out of business. Yeah, maybe. Maybe they're going the way of the dinosaurs. I don't know. R.I.P. Ponderosa Steakhouse. Oh, well. Yeah. Here are some other Cambrian ichnofossils. Now, we don't have good organisms that back these up, and these are from very early in the Cambrian and from places where we don't get good body fossils. We only have those few windows, and those windows are like a particular beach in a particular place at a particular moment in time. They're not terribly extensive and certainly not comprehensive. But here we have something with what looks like radial symmetry buried in the mud. If we were talking about a later fossil, we would say that's probably something like a sea anemone, because they do that. There are some that do that. There are other possibilities. We shouldn't jump to conclusions about body fossils. Yeah, I think that's been clear so far in the course. We definitely shouldn't jump to conclusions about ichnofossils, because we have both more and less information on here. Less information about what it was, more about what it was doing. Yeah. Here are some awesome little trackways. And sometimes you want to look at the edge of the trackway and see if there's a drag of a shell. Then you know you've got a creature that has a sort of an armored covering, and the shell is going to drag on the edges as they move forward, and their legs will be inside where you essentially don't get hurt. The chevrons are going to point in the direction of movement. Imagine you're like a figure skater or something, or like a speed skater. Your skate goes out and to the side, and that's how you propel yourself forward. So that's what's going on here. We're propelling ourselves forward this way. Yeah, there are multi-lobed things far before there was anything, we think, like a starfish. This is probably a multi-lobed sort of feeding trace of some sort. But there are later traces that actually do come from echinoderms that are relatives of things like starfish. Starfish actually get a pretty late start. They're fairly recent. Things like brittle stars are a little closer to their ancestors, but even those things are far younger than. Oh, there's a whole range of weird echinoids. We will get to those when we get to the echinoid chapter. You'll be amazed. They're fantastic. Here's a nice little, looks like a Cruziana. Here's an old Hamia. And these are where there's like a worm in the center that's reaching out and grabbing something to bring it in, or scraping the mud around itself, scraping maybe the bacteria off the mud. And yeah, you get these as extremely fine grained, really detailed fossils. And we don't know what the organism is, so we have a pretty good idea what it did for a living, sort of reaching out and raking something back toward itself. Yeah. So, review questions. What's an ichthyofossil? You know what an ichthyofossil is now. These are trace fossils. They can be traces of anything, from a part of the body to some sort of impact on the environment that's made by a living thing. Yeah. What's Scolithos? That's Scolithos. Series of long, straight tube ichnofossils that you find very, very abundantly at the start of the Cambrian. Very abundantly in some places, not everywhere. And so they have been used as a marker of now you're in the Cambrian when you're looking at the rocks. What are some common types of ichnofossils? Well, yeah, think. What's a Diplochnides? Go look it up. What's a Cruziana? Go look it up. What's a Rusophycus? What would that look like? And what sort of organisms would make those? Trilobites are going to be the most common, because trilobites are the most common in the Paleozoic, which is where most of our study is going to be concerned. But yeah, you can get these sorts of traces from other marine arthropods. You've got to have bilateral symmetry, jointed legs, and you've got to want to bury yourself or sort of cruise along in the bottom layer or the top layer, the transitional layer between the mud and the water. What types of information do we get from ichnofossils? Behavior. Think of those stories that we mentioned back there. The Limulus death march. The little bivalve that burrowed around the sand, around the hill, and then boop, yeah, stuck itself in. Think of the dead bivalve that got swarmed by those worms. Yeah, corpse-eating worms. Oh, disgusting. What do they tell us about the Ediacaran Cambrian boundary? Well, you don't see those burrower fossils until immediately after the Ediacaran organisms go away. So the two are probably linked. Either something that we can't really read in the fossil record happened that knocked out the old ones, or more likely, this is just a function of biological competition. As a new way of life comes in, where creatures are burrowing into and better at consuming the biofilm, these large biofilm mats that used to support Ediacaran organisms go away, and there is basically no comeback. There's no way these things can continue to exist. Yeah, so that is the idea right now. Check back in a year, and probably it has changed. How are ichnotaxa named? With an ichnogenus and an ichnospecies. Yeah. So we name them as if they were organisms, even though they were made by organisms, and even though one organism can make multiple ichnotaxa. Think Diplochnides, Cruziana, and Rusophycus, all made by the same trilobite, potentially. And then here's a riddle for you. Man, you need a sphinx sitting on a mountain to ask something like this. What type of rock often holds ichnofossils, but rarely contains body fossils? Yeah, and the answer would be, well, that's sandstone. Sandstone, you will very rarely find a fossil because, as we saw in the rarefaction lecture, when organisms are exposed to the action of waves that create and move around sand, organisms do not last long. Even really hard organisms like hard corals that are made of literal stone are broken down by the incessant, repetitive, grinding, grating action of waves. The beach is a dangerous place if you stay too long. Stay in school, kids. All right. Stay off the beach. Oh my gosh. Yeah, you don't want that nonsense. All right. Thanks very much. This has been Ichnofossils.